Well, thanks very much for the introduction and for inviting me and giving me the opportunity to tell you guys about some of my research. So yeah, this talk is going to be about, what is the essence of quantum theory? So maybe we should talk about what that means. So for me, this means, what's the precise conceptual innovation that quantum theory has over classical theories? Why is it important? Well, there's both foundational and practical applications. So in the foundation side, there's certain topics where we don't know how to apply quantum theory. Okay, so for gravitational physics, for example, it's unclear, what should a quantum theory look like. But also I'd say there's a lot of classical formalisms where we want to look at the quantum analog and we don't quite know how. So if you consider like the cellular automata model of computation, what's the right quantum analog of that? Or various concepts in machine learning, or the formalism of causal inference, or algorithmic information theory. If you want quantum analogs of any of those, you do need to commit yourself to sort of understanding what's the conceptual innovation that quantum theory represents. And on the practical side, if you get the essence of quantum theory wrong, then I would say you're less likely to identify quantum over classical advantages for information processing. So it's another good reason is sort of for the quantum technology applications. So I'm going to be talking about that question, the essence of quantum theory, in the context of interference phenomena to begin with. And so this is the beginning of this project goes way back to about 2005 and some joint work with Matt Leifer. It never got written up, but last year, Lorenzo Catani and my former PhD student, David Schmidt, finally persuaded us that it was time to finally write it up. And in the process, we learned a few new things. So I'm going to tell you, I hope to get around to telling you, what came out of it more recently. But let's jump right in. And I want to talk about the phenomenology of interference that people typically say is surprising and resists classical explanation. I'm going to call that the trap phenomenology of quantum interference, which stands for typically regarded as problematic. But of course, I'm going to suggest that it's not problematic, that you can understand it from a classical perspective. And so it's a trap to think that this is the actual surprise of interference. So that's why you should remember it's this particular phenomenology. And the story is one that you're going to be familiar with, which is that if you just think of a double slit and you have photons or electrons coming out the double slit, then if you don't look at which slit the particles went through, you'll get the interference pattern. If you do look, the interference pattern will be destroyed. And so many people have sort of described what's puzzling about this. I'm going to give you Feynman's presentation from Feynman Lectures on Physics. So if you think that it's a wave, then you can explain the interference phenomena well. But now, how do you explain the fact that you only ever see one detector fire at the two slits? You don't see both. If it were like a water wave, you might expect some influence at both of the slits. Meanwhile, if you think of it as a particle, then you have the problem of explaining the waves. But moreover, the story goes that if it is a particle and you only have a detector in front of the bottom slit and you don't find the particle there, so now the particle definitely went in the upper slit, then here's the puzzle. That particle needs to know whether it's allowed to arrive at points in the screen where there are nodes in the interference pattern. But to do that, it needs to know whether there was a detector in front of the bottom split or not. And it never spent any time in that region. So how could it possibly know how it's allowed to behave at the screen, given that it passed through the upper slit? So that's the basic story. Feynman says that this is impossible, absolutely impossible to explain in any classical way. It's the heart of quantum mechanics, the only mystery, the basic peculiarity, and the essence of quantum theory. And this is what you read in a lot of textbooks and popular science expositions of quantum theory. And what I want to try to persuade you of is this is not right. In fact, the trap phenomenology can be explained in a totally classical way. Okay, I'm going to focus not on the double slit experiment per se, but on the Mach-Zehnder interferometer instead, which has exactly the same sorts of problematic features. So what's going to replace the case of two slits that have no detectors is the Mach-Zehnder interferometer, where you have a phase shifter on one of the paths. And so now, if I've chosen the path lengths appropriately, when the phase shift is 0, I can have all the excitations coming out the left output port. And when the phase is pi, they all come out the right output port. And the fact that one of the ports is dark is the analog of having those nodes in the interference pattern. Meanwhile, the analog of putting a detector in front of one of the slits is putting a which-way detector on one of the paths of the Mach-Zehnder. And what that does is it destroys the interference pattern, and now I see 50-50 statistics for the two output ports. I don't have a clicker, so I'm going to just keep walking back and forth. So there is a clicker. It's gray thing. Oh. And is it hooked up to my system, I wonder?
Maybe it's this one.
Okay, I'll try. Oops.
This always happens. You just need to do the mirroring again, I guess.
Yeah, and then which way?
So this is the clicker part, and
Okay.
this is the light thing.
Okay, very good. That's going backwards or forwards?
This one is going forwards, this one is forwards, and this one I think is the light.
And what's backwards?
Backwards is the lower one.
Oh, okay.
And the light is weird. So if
Oh,
you
yes.
stand in front
Okay.
of it
Great.
goes to-
Thank you. All right. Sorry about that. Okay, so yeah, let's move forward. There we go. So I'm going to model, I'm going to sort of explain, where that phenomenology comes from the formalism of quantum theory, using a kind of second quantized presentation. So I'm going to use Fock spaces for each of the modes, and I'm only going to care about the cases where I have vacuum or a single excitation. So it's basically like a qubit in Fock space. So this is the notation for the vacuum and single excited states, 0 and 1. Those are like the poly Z eigenstates. And I can have a complementary basis, plus and minus, associated with those guys. And so now, if I look at a pair of modes, this is a basis of the occupation number eigenstates. But I'm going to stick to the situation when there's only a single excitation in the interferometer. So that takes me down to this two-dimensional subspace here, 0, 1, and 1, 0. And I can have superpositions of that and still maintain this only occupation number 1. So the 50-50 beam splitter in this sort of formalism is just the unitary that takes this 1 tensor 0 state to the superposition of it being, the excitation being on the right or the left. So it basically acts like a Hadamard in this two-dimensional subspace. So if I follow through the whole evolution, I start out with occupied tensor vacuum, 1 tensor 0, apply the beam splitter, I get this entangled state. If the phase is 0 here, that just acts as identity on both modes. I'm left in the same entangled state. Now I apply the beam splitter again. I'm back to my original state, 1 tensor 0. So I see everything come out of the left mode. Whereas if it's a pi phase shift, then that's like the poly Z acting, changes the relative phase between those two modes. Now that final Hadamard beam splitter transformation takes me to 0 tensor 1. And so everything comes out the right mode. Meanwhile, if I have a detector here, and I focus on the case where I don't see the excitation, well, that's just represented by the projection postulate, where I project onto the vacuum on the right mode. I have identity acting on the left mode. The only term here that has a vacuum on the right mode is this term, so I renormalize, I get 1 tensor 0, the particle's on the left. Now I go through the beam splitter, I'm back in the entangled state, I have anti-correlation between where I find the excitation, equally likely to be found on the left or the right. Okay, there's a nice version of that phenomenology that's kind of dramatized in what's called the Elitzur-Weidmann bomb tester problem. And the idea is that you manufacture these bombs whose triggers are sensitive to a single photon. And the task is have a bomb which is good, because the manufacturing process sometimes generates duds that have no trigger at all, like this one. And the problem is if you just try to check, the bomb explodes and you don't have the bomb anymore. So what you do is you put the bomb and you line up its trigger so that if it's there, it's in the right path. And now this case here, where the bomb's a dud, corresponds to interference, and so everything comes out the left output port. Whereas over here, it's like a measurement. And in those cases, so sometimes the photon's measured and found here, the bomb explodes, but half the time it doesn't explode, which means it's found that it's on the other path. And in that case, you get no interference, which means some of the time, the photons come out the right port. So whenever you see the photons coming out the right port and the bomb has not exploded, you know it was a good bomb, because if it had been a dud, you never would have seen it come out the right port. Okay, so this is just a dramatization, and just like Feynman said, the mystery is, well, if the particle really went left, how could it have possibly known whether the bomb was a dud or a good bomb, right? It needs to know to be able to determine whether it's allowed to come out the right output port or not. Okay, and so that's the mystery. Okay, so I want to now give you the classical model that can reproduce that phenomenology. So we call it the toy field theory, because it's basically built on a toy theory of mine from that went on the archive in 2004. It's published in that paper. And that's basically a classical theory that reproduces some of the phenomenology of collections of qubits when they're processed in ways that are essentially like the stabilizer formalism. And I'm just going to take that and apply it to these Fock-space qubits on the different modes. That's all that's going on here. So if you're familiar with the toy theory, the next part will be pretty straightforward. So here's the idea that every mode in this classical theory has some physical state, and the physical state is denoted lambda, and it has two properties. It has a number property, an occupation number, and a phase. So these are well-defined properties. They always take a particular value, 0 or 1. So the discrete occupation number, discrete phase. You could have called the phase 0 or pi, but I'm just going to use the binary variable for it. So it's like every mode has this, so it's like a field, but the field is a vector-valued field with these discrete coordinates. And then you say, well, that you can't have any old distribution over these physical states. You have what I called in my paper an epistemic restriction, where you can only know the values of a set of Poisson commuting variables. So these state spaces have a symplectic structure. They're phase spaces. You can identify which variables commute relative to some discrete Poisson bracket. And so you can only know those guys, and everything else you have to be maximally ignorant of. So for example, if you just have a single mode, well, number and phase, they don't commute. They don't Poisson commute. But you could know just the number. And so for example, you could know that the occupation number of that mode is 0, and then the phase has to be completely unknown. That's the analog of this vacuum quantum state. Or you could know that the number is 1 and the phase is unknown, and that's the analog of the singly excited mode. But of course, you could know the phase instead. So now you could know the phase is 0, and then the occupation number is unknown, 0 or 1. That's the analog of this plus state, or the case where you know that the phase is 1. If you look at pairs of modes, so in this interference interferometer, I'm going to have a left and a right mode. Each mode has the same degrees of freedom. So now I have a local number and phase for each of the two modes. So this is a 4-dimensional phase space. So now I can have more interesting sets of Poisson commuting variables, like the number on the left and the number on the right. I can know those simultaneously. So if I know that on the left, the occupation number is 0, on the right, it's 1, that's the analog of this product state. The local phases, in that case, are completely unknown. Or I could know that the excitation is 1 on the left and 0 on the right, and that's the analog of the other product state. There are, however, more interesting possibilities involving sort of collective degrees of freedom of the two modes. So a different set of canonical variables, different from the number on the left, the phase on the left, the number on the right, the phase on the right, is one where I've combined some of these variables together. So I've taken the sum mod 2 of the left phase and the right phase, the sum mod 2 of the left and right occupation numbers, and I'm just going to call those the relative phase and the relative number. So this relative number is going to be 1 because I'm only allowing the cases where only one of the two modes is excited. So 0 plus 1 is always going to be 1. So it turns out that this relative phase and this relative number are an example of a Poisson commuting set. So I could know both those values. But then the number on the left is unknown and the phase on the right is unknown. So this is a situation where I really know nothing about the local guys, but everything about the relationship between them. So what's the sum mod 2 of their phases? What's the sum mod 2 of their local number? And that's the analog of these entangled states. There's situations where you have knowledge of the correlations between the two modes. Okay, so that's the kinematics of this theory. What's the dynamics? Well, I only need to tell you how these basic components of the interferometer work. So this is the beam splitter. So you have, for each mode, these internal properties, and we want to know how do they get processed. And it's just some function, right? So this is the output number and phase of each of the modes as a function of the input number and phase of each of the modes. Okay, so it's just that specific function. It's a little bit easier to think about that if I write it in terms of this alternative set of canonical variables, because in that basis of the phase space, the relative number doesn't change. It's always just 1, right? So I'm always having just a single excitation. The phase in the right mode doesn't change. And all that happens with the number on the left and the relative phase is that their values are swapped. That's it. So in this model, the beam splitter is extremely simple. It says, which way is the excitation going to come out? Answer, it just tracks what the relative phase is. If the relative phase is 0, it's going to go left. If the relative phase is 1, it's going to go right. What's the relative phase at the end? It just tracks what the number on the left was. If that was 0, the relative phase ends up being 0. If it was 1, the relative phase ends up 1. That's it. Okay, the phase shifts are even simpler. I'm always doing nothing on the left mode, so that's just always going to be identity in both cases. And then as I toggle between phase 0 and phase pi, phase 0 just corresponds to an identity. Phase of pi just corresponds to taking this, the sum, adding 1 to this discrete phase. So it's just flipping the phase. That's all that the pi phase shift does. Okay, so let's see how we reproduce the phenomenology of the case with the phase shifter. So I start out over here with the number on the left being known to be 1, which means the number on the right is 0. Each of the local phases is therefore unknown, which means that the relative phase is unknown. So that's my knowledge initially. Now I apply the swap rule, which says that, the value of the number on the left now becomes the value of the relative phase. So now I know that the relative phase after the beam splitter is 1, but I've lost my information about the number on the left. I'm now uncertain about that. So that's just a probability distribution over the physical states here, and it corresponds to this entangled state. And then, if the phase shift is 0, I just do identity. I'm left with the same state of knowledge. The swap rule ends up swapping those two guys, so I'm back to knowing for certain that its occupation number on the left is 1. So I predict that I will always see the excitation come out on the left, which is what I need to happen. Meanwhile, if the phase was pi, things proceed as before initially, but now I'm doing a phase flip. I'm flipping the phase on the right mode, which means that the relative phase is also going to flip, right? Because the phase on the left mode has stayed whatever it was. And so the relative phase flips when I toggle either of the local phases. So now I'm left in this new state of knowledge where the number on the left is unknown, but the relative phase is known to be 0. But now I apply the swap rule because I'm going through the beam splitter again. So now the number on the left becomes known to be 0. So now I know, oh, the excitation came out on the right, and the relative phase has become unknown. So it predicts that I'll always see the excitations coming out on the right. Finally, how do I model the detector on the right mode? So this also follows from the basic mechanics of the Toy theory. And the idea is that when you do a measurement on the right mode and you learn that, say, the occupation number there is 0, you have to Bayesian update. You have to say, all right, whatever probability distribution I assigned ahead of time, I'm now going to assign 0 probability to all the physical states that had the number on the right being 1. I'm going to be left just with the cases where the number on the right is 0. And because of the conservation of number, that means I can infer that the number on the left was 1. But then there's also a step where you randomize the phase of that R mode. So with probability half, you leave the phase the same. With probability half, you flip it. Okay? And that's just a feature of this model, and it preserves this restriction. If I didn't have a randomization of the phase, then I could measure number and then phase immediately after and learn both. And that's not allowed. Okay, so that's how it works. So it means if I look at the case where the detector is in place, I start off the same way. I know the number on the left is 1. The relative phase is unknown. Apply the swap rule. And now I learn that the number on the right is 0. So I started out knowing nothing about the number on the left, but I learn now that the number on the left has to be 1. And although I started out knowing the relative phase was 1, I've randomized the phase of the right mode. So now I've lost my information about the relative phase. The phase of the left mode hasn't changed. It's far away. But I've become ignorant of the relative phase. I apply the swap rule once again at the final beam splitter. And now it becomes the relative phase that's known to be 1. And the number on the left is unknown. And so I expect to see 50-50 statistics. I'm still only going to find the excitation on one of the two sides because of the conservation rule. But I can't predict which side it's going to be. So that reproduces the basic phenomenology just in terms of these physical states evolving according to these simple functions. And if you ask, well, how do you explain what was going on in the Elitzur-Weidmann bomb tester? How did the particle know? The answer is it isn't a particle. We have two modes. Those modes are the entities that carry properties, and they have not only an occupation number, but a phase as well. And so when the occupation number on the right mode is 0, it still has a binary degree of freedom, its phase degree of freedom. And when this bomb has a trigger in place, that even though the occupation number is 0 here, half the time it flips that phase. So what happens when you get to the second beam splitter, if the phase hasn't been flipped, it continues coming out the left. If the phase is flipped, it says, now I must go out the right. And that's why the good bomb destroys the interference and allows it now to come out the right. So it's the idea that I think the problem with the old way of thinking about this is that if you think of quantum states as representing reality directly, then the only kind of reality a quantum vacuum state seems able to represent would be the state of nothingness. There's nothing there. And nothingness can't carry information. So it couldn't tell you whether this bomb was a dud or a good bomb. But if you think of a quantum state as a probability distribution over physical states, and in particular, the vacuum quantum state is just one of those guys, so that occupation number 0 still has this underlying binary degree of freedom. It can still encode information even though it's a vacuum quantum state. Okay, so the punchline is that a mode that's unoccupied can still carry information through its phase. So this kind of model can also handle the quantum eraser experiment. So let me briefly remind you what that is. So there, instead of a detector on the right mode, you couple coherently to some auxiliary system A with a controlled not operation. And then so you start out A in some particular basis state A naught, and then you either measure the A naught A1 basis, I should say it's a qubit, or you measure the complementary basis, A plus A minus. So the control knot acts in the following way. So this guy starts out in A naught. If the mode R is unoccupied, then the auxiliary system stays the same. If it's occupied, the auxiliary system gets flipped to the A1 state. So now if I think about that, if after this C naught, I measure the A naught A1 basis, the case over here, then I'm just learning what the occupation number of the right mode is. So it's just an effective measurement of the occupation number of the right mode. And if I measure instead the plus minus basis, well, here's the entangled state that comes out of the control knot for arbitrary state on the right mode. And if I now collapse to the 0 plus 1 state on the auxiliary system, I get back to the alpha 0 plus beta 1. So that's like applying the trivial phase shift, just identity. But if I collapse to the A0 minus A1, I come back to this, but with a negative sign. So it's effectively like applying that pi phase shift. So the case where you're measuring A plus A minus, which outcome you get is like specifying whether I'm doing a 0 or pi phase shift on the right mode. So that means that I can think of the quantum eraser where I happen to get the A naught outcome as just like this experiment where I don't detect the particle here, and the case where I get the A1 outcome, I have detected the particle. The case where I measure A plus A minus and I get the A plus outcome, that's like the phase shifter with phase 0. And the case where I get A minus is like the phase shifter with phase pi. So that's all that's really going on. But the thing that people point to as surprising here is that because they think of this choice of whether to do a phase shift or measure which way information is somehow impacting the reality inside the interferometer, then there's this puzzle that, if I get to delay the choice of what I'm measuring on this auxiliary system to much later, it's somehow influencing the reality inside the interferometer in a kind of retrocausal, backward in time, mysterious sort of way. That's why it's supposed to be sort of even more mysterious than, say, the Elitzur-Weidman problem. But now let's see what the toy field theory can do for you in this context. So I need to, again, specify a kinematics and a dynamics for this auxiliary system now. So I treat it just the same way I would in the original toy theory. It's just got a discrete position and a discrete momentum, kind of internal degree of freedom. I'll label the position values as A naught and A1. So that's analogous to those quantum states. The momentum, A plus and A minus. They're just binary variables. And now this is what the control knot operation looks like in this theory. So the analog of starting out in the A naught ket is starting out with knowing that this Q variable takes the value A naught, and therefore knowing nothing about the discrete momentum. And then this is the function that describes the C naught. So the position of the A system gets translated by the initial occupation number of the R mode. That's what that plus n is. Meanwhile, there's a back action. The phase of the R mode gets translated by an amount that depends on the momentum of the A system, the initial momentum of the A system. Okay, so if you measure finally at the end, at the output, what the position of that auxiliary system is, which is the analog of measuring this basis in the quantum theory, you can learn the number on the right. Why is that? Because you already knew what the input Q value was. It was A naught. So if you measure the output value, you know that the sum of those two values allows you to infer what the input number was on the right mode. And of course, that doesn't change because the output number is the same as the input number for the R mode. So you've effectively learned the occupation number in this way. But in so doing, you've randomized the phase. Why? Because the phase of the R mode is translated by something that depends on the initial momentum of the A system, and that's unknown. So it's equally likely to have been left the same or flipped. So it's just like if you had come and directly done a measurement of occupation number, you learn the occupation number, you randomize the phase that's there. You've just done it in this way that couples to system A. Meanwhile, if you measure P, the output momentum of that system, then if I look up there, you learn what the input momentum was, because the output momentum is the same as the input momentum. And therefore, you learn how the phase was shifted, whether it was shifted by 0 or 1. Because remember, the phase is shifted by the initial momentum here. You don't learn the number, so you remain ignorant of that. But you learn whether a 0 or pi phase shift was applied to the right mode. And so in that case, if you consider only the cases where you get the A+ outcome, you expect that that corresponds to the case where I would just have phase 0 here, which means everything comes out the left. And if I focus on the cases where I got the A- outcome, it's like the case where I'd have the phase shift pi here, everything comes out the right. And that's exactly what the quantum theory predicts, that when I sort the data by whether I got the A+ or A- outcome, I recover the interference, the two types of interference. And so what's happening here is that it's not the case that the choice of measurement on A is changing the reality inside the interferometer. All along, these two modes had occupation number and phase degrees of freedom, and all that changes in your choice is what you managed to learn about them, right? So you always had an ensemble, some of which were going left and some of which were going right. And over here, you managed to learn information that allows you to sort the elements of that ensemble into all the cases where they went left and all the cases where they went right. And so in those sub-ensembles, you see the interference. Whereas over here, when you focus in on these outcomes, you get a mixture of the two cases and you don't see interference. But all that's happening is you are updating your knowledge about the internal degrees of freedom. Okay, so let me sum up this part, that there's a lot of claims that are made about the trap phenomenology. Here's some of them. Many people say it forces us to the conclusion that there's wave-particle complementarity, that we cannot explain what's going on here in terms of a wave picture and a particle picture simultaneously. It can only be one or the other at a given time. Well, in this theory I just described for you, the modes have a particle-like property, which is occupation number, and a wave-like property, which is their phase. And so there's no sense in which the operational phenomenology forces you to some conclusion about complementarity. No, the operational phenomenology is consistent with both these wave-like and particle-like properties obtaining. Another conclusion, people claim that this forces you to grant that there's some sort of weird observer dependence of reality, that whether the particle ends up being a wave or a particle depends on what you choose to measure on it. Not the case here. It has a particular kinematics all along, and all that depends on what you choose to measure is what you can learn about those physical states, not what they are. And then finally, some people claim that you cannot explain some of this phenomenology using local causes. So for example, in Elitzer-Weidman, some people say that, well, we explain it, that the particle finds out about the bomb through some non-local influence. Or in the quantum eraser, it's thought that there could be a backward in time causal influence. But as I said here, the explanation I described in terms of this, all those causal influences were local. So that the randomization of the phase on the right mode was due to an intervention on the right mode. And there was no influences across space or backward in time. Okay, so the first lesson, therefore, of this toy field theory is just to sort of further provide evidence that the toy theory provided, that a lot of phenomenology of quantum mechanics is most easily understood by thinking of quantum states as like probability distributions over classical states. So quantum states are epistemic. But as I said, we sort of realized something when we came back to this project, which has sort of got me excited, which is I think there's a lesson here for how to think about the conceptual distinction between first quantized and second quantized descriptions of a given experiment. So let me tell you about that. So I would say a very conventional view on how we should think about that distinction is really about what are the entities and what kinds of properties do they have. So in a first quantized description, we tend to think of the entities as particles, and their properties are a motional degree of freedom. So they have positions and momenta, right? So these are things, properties of the particle that can change. Its position is a dynamical variable. Whereas in the second quantized approach, the entities aren't particles, they're modes. And these modes are now parameterized by position. So every different position is not a dynamical degree of freedom anymore. It's just a label for a different mode. And the kinds of properties that modes have, I'll call excitational degrees of freedom. Things like, occupation number or local phase. So that's usually how we think about this distinction. But I'm going to suggest that there's a different interpretation that comes out from this toy field theory. So let's think about how we would describe the interferometer in terms of a first quantized approach. So I have a discrete position basis now. So I imagine there's a particle, it can go right or left, so it has a qubit degree of freedom, this which way degree of freedom, and there's a complementary basis of superpositions of that. I can recover that first quantized description in the standard way from the second quantized description by just identifying the case where it's the right mode that's occupied as that R ket, and the case where the left mode is occupied as the L ket, and the superpositions are what map onto the complementary basis. Okay, now let's see what it looks like in this toy theory. So you can do the same thing. You could write down a toy theory of the interferometer that just says there's a particle and it has a positional which way degree of freedom. But now, unlike the quantum case, it really has that degree of freedom. So the which way variable W is either L or R. It's one of the two possibilities. And there's also a kind of canonically conjugate momentum, which I'll call theta, which has, again, one of two possibilities, which I'll call just 0 and 1, a kind of discrete phase. And I can recover that description from the toy field theory I showed you, which I think of as sort of the second quantized toy theory, just by using this set of canonical coordinates where I have the number on the left and the relative phase. And it's the relative phase that maps over to that theta, and the occupation number on the left is what maps over to that which way degree of freedom. This relative number is fixed to be 1, because whenever we go over to the first quantized picture, we always have to demand that the total number of excitations is 1. And what I'm doing in this transition is just coarse graining over this phase on the right. I'm just ignoring what value that has. So in this toy world, this transition from second quantized to first quantized is just a coarse graining. It's ignoring some of the degrees of freedom. And the reason I can reproduce everything I told you earlier just in terms of this W and theta is because they track the number on the left and the relative phase, and everything I described for you about reproducing the operational phenomenology was only a discussion about what that left number and the relative phase were. It was always a story about those two guys. So I can just repeat the same story in terms of W and theta. So, you know, it would look like this, where I've just replaced everything with their first quantized equivalents. But now here's the key point. If I had only done this, right, if I said this is my model, then there would be a puzzle, which is, remember that when the detector is on the right and it didn't detect, I learned that the which way variable is left. It didn't go to the right, it went to the left instead. And I randomized this theta variable. Now, if you're thinking particle picture and you say, okay, the theta variable, that's the property of a particle, it should probably live on the particle. And if the particle went left, then how could a measurement on the right possibly randomize that theta variable? That theta variable is nowhere near it. It would have to be a non-local influence. So if you forget that theta is really just coarse-grained information about phases of two local modes, it's really a global property of the pair of modes, which I can manipulate by changing the phase of the left or the right mode. If you forget that, then it looks like non-locality. But if you say, no, there's no particle here that has a which way degree of freedom and an internal phase, there's just two modes with their degrees of freedom, then you could say, all right, the picture's fine, I just have to remember it's a coarse graining of a fundamental mode ontology. So that's the punchline. That the second lesson is that the second quantized description is the fundamental one, and it describes an ontology of modes and their excitational properties. The first quantized description is just a coarse-grained description of that very same mode ontology. It is not a description of an ontology of particles. And I think that thinking that it is what leads many of these interference phenomena to appear puzzling, because we have this sort of particle bias, and things don't look local relative to that. All right, so I want to end by saying just something about the opposite side of the coin, which is if all of this is classical, what is it, if anything, about interference phenomenology that does resist explanation in terms of the classical worldview? I've been using sort of a bare bones notion of classicality, which is that the kinematics and the dynamics are basically sets and functions. That's all I've required for my classical model thus far, and that, you know, inferences in the face of uncertainty are just done by classical probability theory. But if you want to start proving no-go theorems and saying things are really non-classical, you often, need to make some additional assumptions, like the locality assumption in Bell's theorem. So I'm going to do that. I'm going to endorse what's called the Leibnizian methodological principle, which basically says that if two things are empirically indiscernible, then you should model them the same way in your ontological theory. And that's just a fancy way of talking about the principle of generalized non-contextuality, of which Bell's notion of local causality is a special case. So if you don't know about generalized non-contextuality, don't worry about it. I don't have time to go into it. Leibniz's principle and non-contextuality are described in these papers. But I just want to tell you, if you take that, it's a very conventional notion of classicality. You can derive no-go theorems if you add this sort of assumption. So let me just remark that the whole toy field theory I told you about earlier is generalized non-contextual. I showed you that it was local, but you can also show that it satisfied this notion of non-contextuality. So it satisfies this higher bar of classicality. But now you want to ask, well, what is it that resists this kind of model? And there's a cheap and uninteresting kind of answer, which is just take your favorite proof of contextuality, whatever it is, and translate it over into interference language. So there are proofs of my generalized notion of contextuality that work for a single qubit. So I could just build that in an interferometer, or make it a dual rail qubit. And now I have an interference experiment that witnesses contextuality. But that's kind of boring because it's just saying what we all knew in the language of interference. The more interesting kind of answer is, can you find some aspect of the operational phenomenology of interference that was of prior interest to researchers, things that people already looked at and said, this is characteristic of quantum interference, and that witnesses the failure to admit of a non-contextual model. So that's what people should spend their time doing when they're looking for sort of non-classical aspects of a given phenomenology. So one answer to that question is basically the functional form of wave-particle duality relations. So wave-particle duality relations are trade-off relations between fringe visibility and path distinguishability. So you imagine this same interferometer, you think of the early stage as a kind of preparation for this dual rail system, or this pair of modes. And here I'm going to imagine a broader set of preparations. This beam splitter doesn't have to be 50-50 anymore. It can have variable reflectivity. And then you imagine finishing the beam splitter in the usual way with the 50-50, finishing the interferometer with the 50-50 beam splitter, or taking out the beam splitter altogether, in which case you're just asking whether it's on the left mode or the right mode. So those are the sort of two measurements you might do on this preparation. And if you sort of ask for the bias in the outcomes, you get the definition of fringe visibility and path distinguishability. And what you can show is that they satisfy that relation there, that the sums of their squares is less than or equal to 1 in quantum theory, and you can saturate it with quantum states. So the points 1, 0, and 0, 1 are the cases we've talked about up till now, where for example, if my preparation procedure is the 50-50 beam splitter, so I prepare a coherent superposition, then I'll get perfect fringe visibility, but no ability to predict the outcome of a Witch path measurement. Whereas if I leave this beam splitter out or put a 100% reflectivity beam splitter, then I'll have perfect predictability about this measurement, but no predictability about this measurement. Those are those two extreme cases. I explained to you how they can be explained classically. Question is, what about the cases in between? What if I make the beam splitter somewhere between 50-50 and 100 or 0, like 75%, 25%? Well, it turns out if you do that, then you do get evidence of non-classicality. What you can show is that in a non-contextual model, you also have a trade-off between fringe visibility and path distinguishability, but it's a linear trade-off. And so it includes the endpoints, but it does not include these points on the circle. And so anytime I set that beam splitter with some intermediate reflectivity, and I see that the sums of the visibility and the path distinguishability is greater than 1, I have a proof of contextuality. I have evidence of non-classicality. So this article is going to appear soon on the archive. Let me wrap up by mentioning that although I've been talking about interference phenomenology, it's the same story sort of across many different phenomena in quantum theory. So in quantum interference, we say, well, the faux kind of non-classicality is just the trap phenomenology. That's not really non-classical. The genuine type of non-classicality is this precise functional form of the wave-particle relation. So what about uncertainty relations? So it turns out that if you think that the non-classicality of quantum mechanics is the fact that you can't learn certain pairs of variables like Z spin and X spin simultaneously, well, you can explain that in these classical-like models. Like, it's easy to build classical models where you can't know both of those variables. But what you can't explain is the precise functional form of those uncertainty relations. So in this paper on the bottom, we show that it's very similar, that the non-contextual bound on the trade-off between the predictability for your X measurement and the predictability for your Z measurement, as quantified by the absolute value of their expectations, that obeys a linear trade-off in a non-contextual theory, but it's this sum of squares trade-off in the quantum theory. And so that witnesses the non-classicality. Similarly, if you think about a bipartite correlation experiment, so the EPR Bohm experiment, which is just Bohm's spin version of the original EPR experiment, is an example. And it's not hard to explain that one in terms of a local hidden variable model, right? Nothing in what EPR's correlate described resists explanation. But if you have Bell inequality violations, then you really can't explain it in this local way. So you don't have a Leibnizian model. And people often give you this caricature where the red is like the local bound, the blue is what quantum mechanics can achieve. And again, we see there's a small difference. I can get up to 75% on a certain Bell quantity in the local model, 85% for the quantum. That's the small gap. It's not the fact that I can have perfect correlations. No, that's easy to explain in a classical model where I don't know everything. Okay, so again, it's a small difference. Here's another example. What's non-classical about state discrimination? Well, often you hear that the fact that you cannot do an error-free discrimination of two non-orthogonal states, that's surprising. Well, it's surprising if you think of non-orthogonal quantum states as being states of reality. Because in all classical theories, the different points in my phase space were distinguishable. But if you think of quantum states as being like probability distributions over an underlying classical space of physical states, then it's entirely natural. If I have two distributions that overlap, then if I sample the physical state from this one or this one, sometimes it's going to be in the region of overlap, and I definitely can't tell you which distribution it was sampled from once you just tell me the physical state's in the region of overlap. So, classical theories can explain the fact that there's no error-free discrimination of non-orthogonal quantum states, but what they can't explain is the precise form of the trade-off between the probability of successfully discriminating them and a measure of how non-orthogonal they were. So in this paper with David Schmidt, we showed that there's a non-contextual bound on the trade-off between S, the probability of discriminating, C, the confusability, which is roughly a measure of their non-orthogonality, and the form of the quantum trade-off, a small gap. And so you can go through other phenomena like cloning, unambiguous state discrimination, weak values in pre and post selection. It's always the same story. The things that we've been told are surprising actually can be explained in these sorts of classical models. But there's some more nuanced feature, something more quantitative about precise trade-offs between particular relations that resists explanation in a non-contextual model. And that's where the genuine non-classicality lies. So all of this can be thought of as sort of a part of a broader research program, which my group and I are engaged in, which is trying to figure out what that thin film of quantumness really is. So for most of the things that we are told constitute the essence of quantum theory, I'm confident that the qualitative features of those typically can be explained in one of these classical models. It's typically important that you make the analogy between quantum states and probability distributions over classical states, not classical states themselves. And these days, I'm very much of the opinion that you also need to make sure that your classical ontology is a wave ontology. It's got to be fields. If you imagine that the classical theory is a particle theory, there's a whole bunch of things you're not going to be able to explain. But that transition from particles to fields is not a transition from classical to quantum, because I can have classical field theories where I have limited knowledge. So those classical field theories with limited knowledge are going to capture a whole bunch of the phenomenology of quantum theory. And the question is, what's left over? What's the quantitative, more nuanced aspects? Because those are the things, that thin film is what we need to be focusing on to really understand what the capacities of quantum technologies are and how we ought to sort of extend quantum theory into new domains. So with that, thanks for your attention.